Alright, so let's move on. We're done with this already. So I've explained that, um, say, the time to go up is equal to the time to go down, given that the surface or the floor is even or is equal. It's not an there's no cliff or anything. So from there, also the distance going up is similar to the distance going down. I mean, not similar, equal. Just think about it. If you catapult yourself going up and then you go down, the highest point from going up to from going down is going to be the same. And the place where you started is also the same place where you'll end up. So, number 4. Soccer player hits the ball, I guess, vertically upward, speed of 12 meter per second. So that's the initial velocity. Because the moment he hit the ball, he or she hit the ball, this is already the velocity. So, and eventually, the moment it reaches its highest point, the final velocity would be 0 because it would go down. So, gravitational acceleration is negative 9.8. Distance is missing, time is missing. But we don't have to look for time because we have this formula where we could use these 3 values. So Vf is 0, Vi is 12, G is 9.8, negative 9.8. Substitute the values, simplify, you get 7.34 or 7.35. Okay, for number 5, a snowball is thrown upward at a speed of 27 meter per second. So how high is the snowball 3.5 seconds later? So actually, I want to solve this problem manually just to be sure, because I'm taking my exam later in regards to this lesson, and yeah, this is quite a challenging question. By the way, this is from my professor. Alright, so a snowball is thrown upward at a speed of 27 meter per second. So let's write first y-axis going up, final velocity we don't know. Initial velocity is 27 meter per second. Gravitational acceleration, obviously it's negative 9.8 meter per second squared. Distance, we don't know either. Time is 3.5 seconds. This is given that you don't know the time when it would hit the ground, like from up to down. But maybe we could use this value to look for the final velocity. Okay, so what we're looking for is this one, and how fast was it moving at that time, in what direction. I think it's this one, but I'm not sure yet. But yeah, let's solve for D. D is equal to VIT plus GT raised to 2 over 2. Distance, we don't know. VI, we know. Time, we know also. The gravitational acceleration, negative 9.8 meter per second squared times 3.5 seconds raised to 2 over 2. Okay, so what is 27 times 3.5? It says 94.5. How about the other one? Negative 60.025 meters. So 94.5 minus 60.025 is equal to 34.475. Precisely. Same answer. So how fast was it moving at the time? So given this time, what's the VF, I guess? I'm not sure. Because there's another formula called D is equal to RT. R is equal to D over T. So what is the velocity given the distance and the time? So 34.475 meter over 3.5 seconds. Rate is, in other words, velocity. Let's see if if the solution is correct. 34.475 divided by 3.5 seconds. That's not the answer. It says 9.85 meter per second. So I guess we're not going to use that formula. I hypothesize that we have to look for VF. Let's see if the number matches. G is equal to VF minus VI over T. Negative 9.8 meter per second squared is equal to VF minus VI, which is 27, over time, which is 3.5. So negative 9.8 times 3.5 is equal to 34.3. Negative 34.3 meter per second, I suppose. Yeah. And this is kind of weird. Why is my value? I think this is the one we're looking for. So 34.3 and 27, you get 7.3, but it's negative. Why is it that in the answer key, the answer is only positive? Oh, wait. I think it's because there's a word down. We're also looking for what direction it's going to. So I hypothesize that the negative means downwards. So instead of writing a negative value, just write the positive value, but write the direction down. Why is it that if it's negative, then it's going down immediately? In the Cartesian plane, in the grand scheme of things, negative can also be going to the left, not just going down. Well, we're only talking about the y-axis. There's no x-axis yet here, so yeah. Again, any creative idea, disregard. This is not the right solution. This is. Okay. It's the same thing. I also looked for the time. It's kinda unnecessary, but I was able to do the job anyways. Alright, so let's move to number 6. This is, I'm also going to answer this manually. If you're thinking I could use the extra space that you're seeing right now here, but for uniformity, let's use it in another page. It's a digital notebook after all. You're not wasting paper. And we're not exactly trying to be that economic in a way. In Filipino, you call it matipid. Okay, so the ball flies straight up in the air. Exactly 4 seconds later, it lands right next to the T. I initially thought it was misspelled as 3. So what I thought was, this is all 4 seconds. But I was wrong. T was a word, something related to golf, and it's basically the surface of the land where the golf ball was initially located at before it got hit. So let's say going up is 2 seconds, going down 2 seconds. Overall, they make up 4 seconds. So let's write that down. Y-axis going up and the y-axis going down. The VF, the VI, the gravitational acceleration, the distance, and the time. Time going up, 2 seconds. Time going down, also 2 seconds. Again, we were able to divide 4 into 2 parts because of the general rule that given a plane surface or an even surface, say you're given a total time, you can just divide it by 2 to calculate for the time going up and the time going down. And the gravitational acceleration going up is negative 9.8. Don't forget the unit, that's important. And going down is the same number, the same unit, but it's not negative. We look for the VI, the VF. So far, we don't know what the distance is. Well, theoretically, they're both equal to each other. So if you find the distance of going up, it's the same thing as going down. But before that, let's settle some things in the VF and VI first. So given that we start from going up, from down to up, the initial velocity is going to be at its maximum, but we don't know the value. VF, the moment the ball is at its maximum height, the velocity final becomes, or the velocity at that point becomes 0 meter per second. And from there, 0 meter per second, in the moment before the ball or the golf ball hits the ground, the VF or final velocity is at its maximum. So we already have a fixed table. Let's see if you could look for the distance. This is what I'm going to do in the exam. So I'm gonna write down all the formulas that I remember. Well, I should remember all. Otherwise, I'm doomed. You already have to create an allowance just in case you make a mistake in the computation. At least you didn't screw up in the memorization part. So D is equal to VIT plus GT raised to 2 over 2. D is equal to VF raised to 2 minus VI raised to 2 over 2G. Those are the 3 main formulas. Let's see what's the most appropriate to look for the distance. We don't know VI, so we can't use this. I think we can use this. Let's see. This is to look for the initial velocity. This sub value is going up, basically. So negative 9.8 meter per second squared is equal to velocity final, which is 0 meter per second, and the velocity initial, which is missing. So we just write the variable, and over 2 seconds. Multiply both sides by 2 seconds, we get negative 19.6 meter per second. Yeah, since this has S, and there's an S here, they get cancelled. So we are left with the unit meter per second, and negative vi. Make this positive. You have the initial velocity. Now, let's I'll just write this. Okay, so let's look for the distance. We now know the vi. I'll demonstrate to you two ways on how to solve for the distance. One way is using this formula, or another way is to use basically this one. Okay, so the first vi is 19.6 meter per second. The time is 2 seconds. The gravitational acceleration is negative 9.8 meter per second squared times the time, which is 2 seconds. And then don't forget the squared. Always don't forget this. Don't make the same mistake as me, and I hope I don't make a mistake later in regards to that. Otherwise, you'll be credited for being careless. There's a raise to 2 there, always. So we have 39.2 negative 9.8 times 2 raised to 2 over 2. We have negative 19.6. Don't forget the unit, by the way. So 39.2 minus 19.6. A while ago, 19.6 times 2 is 39.2. So 39.2 divided by 2 is the same as this, which is 19.6. Let's see if we'll get the same value using this formula. Just to show you the flexibility in trying to solve. You do your way. You find what formula is the most feasible to use, which is the easiest, which is the most efficient, given the time that you have. Vf is 0 meter per second squared minus Vi, which is 19.6, and then 2 times the gravitational acceleration. Alright, so 0 minus 19.6, and then below we have 19.6. The answer is still 19.6. Sorry, this is only meters. So basically, here in the numerator, the meter raised to 2 per second raised to 2 gets divided by this one, which is meter over squared raised to 2. The units are very important. Although you can memorize, for instance, the unit for distance is meters, the unit for gravitational acceleration is meter per second squared, etc., etc. Vf and Vi is basically their unit is meter per second without the squared, but it's also as necessary to know how the units evolve throughout the equation. You don't only solve the numbers, you also know what the story of what happened with the units. So get the reciprocal, cancel, and you get meters left. So that's it. So as you can see, the answer is still the same, and according to the answer you gave, it's the same either. The same too. Same solution. I don't think this is still necessary, but just to be safe, still draw it. You might be asked with a question that asks for a number that falls under this category the moment the ball goes down. I think number 5 is the most challenging. Uh, yeah. Um, so why is it challenging? So as you can see, I looked for the time. You didn't have to look for the time, but I looked for it anyways. And as you can see, it's 2.7 or 2.8. And the time that we're given here is 3.5 seconds, which is bigger. So this is a bigger quantity. So what happens to the snowball 3.5 seconds later? Here, um, the entire duration of the snowball going up is 2.8 seconds. So the snowball here, 3.5 seconds later, let's say 3.5 minus 2.8. Roughly 0. Seconds later, um, let's say somewhere here, this is where the time was recorded as 0. Seconds before completely going down to the ground. You have to calculate the velocity during this time period, which is we eventually found out to be 7.3. And theoretically, from there, if the velocity during this time is 7.3, then the VF, the actual VF, the moment or roughly before the ball hits the surface, is going to be a lot or significantly bigger than 7.3. So that's how you analyze this problem. So that's everything for this video. Thanks for watching. And I hope I ace the exam later. Actually, it's gonna happen in 30 something minutes. Again, thank you.